Can you see my screen now?
Yes, sir.
Okay, thank you. Okay, so let me recall what we did in the last class. So in the last class, we defined simultaneous diagonalization, and then we saw one result. We proved one result that gives us a necessary and sufficient condition to say whether a given set of matrices is simultaneous diagonalizable or not. So what is that? So if suppose we have a family of matrices which is diagonalizable, then this family is simultaneously diagonalizable if the family is commuting. That means if you take any two matrices in the family, then these matrices commute with each other. So that was for simultaneous diagonalization. Similarly, you can talk about simultaneous triangularization also. That means if suppose, let's say, start with the two matrices. Suppose we have two matrices, then when can we say that they are simultaneously triangularizable? That means whether when there exists a common transformation that triangularize both the matrices simultaneously. Or if you want to generalize the question, that means if suppose you have a set of matrices, or you can say a family of matrices, then when can we say that that family is simultaneously upper triangularized or lower triangularized? Okay, so in today's lecture, we will talk about this first, and then I will start spectral theorem for normal matrices and for Hermitian matrices. So that is the plan for today's lecture, but let us first discuss this simultaneous triangularization. The result is again, we'll prove it by induction like we did in the last class. The idea of the proof is exactly what we did for simultaneous diagonalization. So let me first write the statement, and then we'll talk about them. Okay, so at any point, if you have any doubt, you can stop me, you can ask. All right, so what is this result? This result says that if suppose we have a family of matrices, so that means let's say this script A, this denotes the set of n cross n matrices. It's a subset of n cross n matrices over C is, you will know why I'm taking this over C. There is a, you can also state a corresponding result for when you have a set of real matrices, real n cross n matrices. So I'll prove this for C. So if we have a family of matrices, that means a subset of n cross n matrices over C, which is commuting. So if this family is commuting, then then there exists this property of commuting itself uh, sufficient to say that that family is simultaneously upper triangularizable. So if we have a family of matrices which is commuting, then there exists a single unitary matrix, let's say U, of the same size over C, such that U star AU is upper triangular for each A in the family of matrices. Okay? So if the family is commuting, then you can find a single matrix U that simultaneously upper triangularize all the matrices in that family. One thing is clear, that if suppose you have a, so that means the converse of this statement. That means if you have a family which is simultaneously upper triangularizable, then that family must commute. That you can verify. Okay. So why is that true? Can you do that? Oh, that is not true. Sorry, mistake. So it's not true if you if suppose you have a family of simultaneously diagonalizable matrices, it is not necessarily the family need not be commuting. Okay? We'll see one example, but you will also see in the proof. So it is only one direction. Let us make this. Let us prove this. So we'll prove it by induction as we did in the case of diagonalization, simultaneous diagonalization. We will prove it by induction on the size of matrices, that means on n. So we will prove it by induction on n. Okay. So clearly when n equal to 1, this is a trivial case, right? So when n equal to 1, then there is nothing to prove. You can take if suppose all the matrices of size 1 cross 1, then you can take u as then by definition all the matrices are upper triangular, and therefore you can take u as identity, and that is fine. Also, similarly, now suppose n is greater than 1. Suppose n is greater than 1. Again, if suppose if all the matrices in A in this family are scalar multiple of identity, then also it's straightforward, or you can say it's trivial to check. Okay? Also, if you have, let's say, A, if A in this family implies that A is equal to alpha for some alpha in C, then also it is trivial to check, right? So therefore, assume that there exists at least one matrix A such that A is not equal to alpha I for any alpha in C, because it is not a scalar multiple of identity. So let we have a matrix A in this script A, that means in this family, such that A is not equal to alpha I for any alpha in C. So if you recall from previous result, in what we did in the last class, we have started our proof exactly in the same way. So what is our aim as to what is our aim in order to prove this? What we did in the last class in the case of simultaneous diagonalization, we try to like use the fact that this matrix, that family is diagonalizable, and it is commuting. So I took a matrix A there, this kind of matrix, and then since it is diagonalizable, there would be a invertible matrix such that P inverse AP is diagonalizable. Then since this family is commuting, so if you take any two matrices A and B, then you can say that P inverse AP and P inverse BP, these matrices are also commuting. And then from there we get so if I take any matrix in the family, then and if I do if you find this P inverse BP, then we observe that this would be of this would be of this form, right? So block diagonal. And then we realize that each of these diagonal block on the diagonal, they form a like a family of matrices of a smaller size. And then we applied induction hypothesis on these, and then using the transformation matrices for these blocks, we constructed our transformation, let's say P tilde, that simultaneously diagonalized all the matrices in the family. This is what we did in the case of simultaneous diagonalization. In the case of simultaneous triangularization, that means for this proof, we will proceed. The idea is to follow the same lines. The only thing is that here we don't have this diagonalizability condition. So we just have that our matrix is a n cross n complex matrix, and this family is commuting. This is what we are given. Okay. Now, since so, what we will do here also we will try to use the fact that this matrix is a complex matrix. That means the complex matrix ensures that it will have at least one eigenvalue. So we will use the fact, this fact. And the second thing, we will use the we use the property that all the matrices in this family are commuting. Using these two properties, we will try to again write for some matrix. Let's say V. We'll try to write it in some kind of block form, and then for these blocks, I will try to like construct smaller size unitary matrices that simultaneously upper triangularize these smaller families, and using those smaller size transformation or unitary matrices, I will construct the main the desired unitary matrix that simultaneously upper triangularize all the matrices in the family. This is the idea. Okay. So now how we can do that? So A is a n-cross-n matrix in this family such that it is not a scalar multiple of identity. It's a complex matrix, and we know that every complex matrix has an eigenvalue. So we can say that, okay, let lambda be the eigenvalue of A. So lambda be the eigenvalue of A. So this is the notation for set of eigenvalues I'm using. Maybe I can say, write it in place of using this notation. So let's say let lambda be an eigenvalue of A. Okay. It's an eigenvalue, and assume that W be the range space of A minus lambda I. So clearly W is a subspace of Cn, and you can assume since it's a subspace of Cn, you can assume um, a basis for this, an orthonormal basis for this subspace. Say V1 to Vm. This is a basis or orthonormal basis of W. So W is a subspace, so we can assume that let's say V1 to Vm, these vectors form an orthonormal basis of W. Okay? And we can extend this basis to a basis of Cn. Remember what we want? We want to somehow construct, we write this first, basis of Cn. So what we want to construct a unitary matrix V that simultaneously upper diagonalize all the matrices in this family. That means for every A, or let's say for every B in this family, I want this V star BV is some upper triangular matrix. This is what I want. So I'm trying to construct this V. Now what I have so far, I have a set of orthonormal vectors. So using these vectors, I can construct V. So V is a matrix where the columns are nothing but these vectors. Okay, to Vn. So this is clearly an n cross n matrix, and it is also unitary because columns are orthonormal. Okay, so we have a unitary matrix. All right. Now, if I take any let's say B in this, and if I do this V star BV, so let's say V star BV, when I do this V star BV, then what do I get? So let's say if I so let me write it in this way. So if V is denoted by these columns, then V star would be V1 star, then V2 star, row wise I can write them, Vn star, then maybe Vm star, and then Vn star, right? And then V, and V would be V1. This column wise you can write. VM. So when you multiply this, the right hand side would be what? It would be first entry would be V1 star B V1, and the second entry would be V1 star B V2, and so on, right? So this would be V1 star B Vn, and likewise you can write all the entries. Here it would be Vm star B V1, so on up to Vm star B Vm, Vm star B Vn. You can write Vm star V1 star B Vn. This would be Vn star B V1, so on Vm star B Vm. Sorry, Vn star B Vm, then Vn star B Vn. Okay. Now, can you see that some of the entries in this matrix, in the right hand side of this matrix here, some of the entries are 0. Can you tell me which entries of this matrix would be 0 and why they would be 0? So for example, you look at this one, Vm plus 1, let's say for example, Vm plus 1 star V1. What would be this? What would be this entry?
It will be 0.
Why?
So because B V1 is equal to lambda V1s, and they are orthonormal vectors Vm plus 1 and V1. So that is why it will be 0.
V1 would be lambda V1.
So because lambda we have taken as eigenvalue.
But it is an eigenvalue of A.
Oh, sorry.
Right?
Yes.
But something like this, if you can use, we have not used, so in your argument you have not used the fact that these VIs form a basis for range space of A minus lambda I. So look at here if you carefully look at this thing, V1 to Vn. So let me just write this side. So you know V1 to Vm, they form a basis for range space of A minus lambda I, right? So they belong to range space. That means for every Vj, so for every j equal to 1 to m, there exists xj in Cn such that A minus lambda I xj equal to Vj, right? Because they belong to the range space. Now, if you look at this thing here, if you write in place of here bv1, so what would be bv1? Bv1 would be v1 would be A minus lambda I times x1 for some x1, because v1 belongs to the range space, right? But since A and B, they commute, so what would be this? This is same as AB minus lambda I times lambda b x1, which you can write as A minus lambda I b x1, right? But what does it mean? It means that this belongs to this set. This is an element in the range space of A minus lambda I, right? This vector is in the range space of, so that means in W. W is the range space of A minus lambda I. If this is in W, and we know that V1 to Vm, they form an orthonormal basis for W, and then this Vm plus 1, and so on up to Vn, these vectors are orthonormal. So clearly this vector here, since this belong to W, this is in the, this belong to span of V1 to Vm, Now if you take, so this is same as BV1, right? Now if you take Vm plus 1 star of this, then it clearly it would be 0, right? But this is true for all, like if you use this. So is it okay? Is this argument fine? Did you understand why this term would be 0?
Yes, sir.
So therefore, so I'll keep it here so that you can understand later on also why this is true. Because of this, you can say that. So I'll write here. Note that Vm plus I star Bvj is equal to Vm plus I, where note that for I equal to 1 to n minus m and j equal to 1 to m, this quantity is same as b a minus lambda I xj for some xj in Cn, but then this is same as Vm plus I star a minus lambda I Vxj, but since this belongs to W and V1 to Vm, they form an orthonormal basis of W, and all these vectors Vi's are orthonormal to each other. So this implies that this quantity is 0. So basically what you see here, that for any matrix B in this family, so for any B in this family, if you do B star BV, then it would be of this form. So this implies that B star BV would be of the form B11, let's say B12, 0 and B22, where so it would be block upper triangular where B11 is an M cross M matrix, and B22 would be n minus m cross n minus m matrix. Okay, fine. So far I think there should not be any problem. Now we will use the same idea. If you recall again from the previous class, this is true for any matrix B in this family. Now again, since if I take any two matrices, so since A is commuting, this implies that if I take any two matrices, let's say B and C in this A, then product of B and C is same as product of C and D. But then this implies that B star BV, B star CV is equal to B star CV, CV B star BV. What I'm saying is that B and C commute. This implies that B star BV and B star CV would also commute. Right? But then you know what are these V star BV? What would be this? It would be a matrix of this form. Right? So you can write, let's say V star BV would be of the form B11, B12, 0, B22, and similarly V star CV would also be of similar form. Say, and you can write the right hand side also. Right. Now, since these two things are same, if you compare left hand side and right hand side, what do you get? So if you compare left hand side and right hand side in this product, then this will imply that B11 C11 is equal to C11, B11, and B22, B22 is equal to B22, B22. So now you can see that we have a smaller size family of matrices. That means if I consider two family, like let's say A1, A1 is the collection of all such B11 where B belongs to this family A. So what is B11? So if you take any matrix B in this A, then you do this V star BV. You write V star BV in the block form. That means in this kind of form. And then B11 is the 1-1 block of this matrix. You do it for all the matrices in A, and you collect all such matrices. Clearly, this B11 is a smaller size family, and also they are commuting, right? And similarly you can construct A2 also. So and A2 would be collection of all such B22 where B22 is coming from this B in the family A. Okay, so clearly then this family A11 and A22, they are commuting, and therefore now they are smaller size family. So this implies that by induction hypothesis. So here you may ask why, what is the guarantee that they are of smaller size, they are not of same size? You can ask this question, why this family, their size is smaller than n, is less than n. Okay, think about it. So I'll ask this question. So I'm saying here that they form smaller size family of matrices. They are commuting. So now by induction hypothesis, there exists V1, a unitary matrix of size m cross m, is unitary, and a matrix V2 of size n minus m cross n minus m or C, such that Vj star Vj Vj sorry Vj star Vjj Vj is upper triangular for each V in family and J for 1 and 2. Right? So now we have a smaller size unitary matrices, and using these unitary matrices, now we can construct our transformation matrix. That means if I now define, let's say this V tilde, which is this matrix now, V1, V2 on the diagonal, and this. Now then you can verify that, since what is this V? V is the matrix we have chosen here. And this V1, V2, they are the smaller size matrices. But now because of these zero blocks, I have a n cross n matrix here. V1 and V2 are unitary, so this matrix also unitary. Product of two unitary matrices is again unitary, so this matrix is unitary. So V tilde is a n cross n unitary matrix. So if you define V tilde in this way, then this is unitary. Not only that, and for each V in this family, it satisfies the following. If you do this V tilde star B V tilde, then what it would be? It would be V1 star 0 0 V2 star V star BV V1 V2. But then you know what it is this one V11 V12 0 B22, right? But then what it is just V1 star V11 uh, V1 star V12, and this is V2 star V22, and when you multiply from right hand side, it would be V1 star V1 1 V1 0 V2. Now since this matrix is upper triangular, you can say that this matrix is actually an upper triangular matrix. This upper triangular, and you're done. So you have found a matrix V tilde which is unitary, and it diagonalizes, it triangularizes every matrix in this family. Okay? So if we have a family of n-cross and complex matrices which is commuting, then you can always find a, a single transformation matrix, unitary matrix, that simultaneously upper triangularizes every matrix in this family. Now, can you please tell me why? You can see here why this these these families are always of size less than n. So we can use the induction hypothesis provided that these families are of less size. Now, it may happen that one is of size n cross n, another one is just nothing. But why this is not possible here?
Because of our assumption, sir, A is not equal to L5.
A is not equal to L5. Exactly. Because of that assumption, this cannot happen. So it won't be the range space here won't be the whole Cn here. There would be at least one vector which is not there in the basis of W. So because of this reason, this works. Okay, so now you have a way to simultaneously diagonalize a family of matrices, and similarly you can simultaneously upper triangularize a family of matrices. Okay. So let me recall what we have done so far. Uh, we have learned unitary matrices. So I'm just recalling what we have done. So we have learned unitary matrices, and then we saw that they are useful. They are useful in many ways, and are more important than the from a numerical point of view. They have more advantages over the standard similarity transformation. And then we saw that since not every matrix is diagonalizable, what else we can say? Then the Schur's theorem comes into the picture. It says that okay, you cannot diagonalize a complex matrix, n cross n matrix, but you can always upper triangularize it. So Schur's theorem we have, Schur's lemma we have seen. We have seen a complex version of this, and we have also seen a real version of Schur's lemma. So complex version says that you can always upper triangularize it by a unitary matrix, and real version says that if you are starting with a real n cross n matrix, then you can always find a real orthogonal matrix that so that that U star AU is block upper triangular, where at the diagonal you have either 1 cross 1 block or 2 cross 2 block, right? This we have seen. Then we have seen how to achieve this Schur's lemma. That means one can always upper triangularize it using these rotators and reflectors. They are useful in like creating zeros in a matrix. And then we have seen QR decomposition also. QR decomposition we have seen the proof we have seen via several ways. Like one can prove it uh, using Gram-Smith. One can use it. One can use it. One can prove it using via and using arguments of analysis. Then one can use it. One can prove it using rotators and also reflectors. at least when the matrix is a real matrix. But a complex version of rotators and reflectors is also there. And then we saw simultaneous diagonalization, and then we saw simultaneous triangularization. Okay, so we are still in the section of matrix factorization. Now next we will learn spectral theorem for normal and Hermitian matrices, that we will see. And then next we will see, depending on the like how we proceed here, depending on that we will see first SVD, that means the singular value decomposition and polar decomposition of a matrix, and then we will see Jordan canonical form of a matrix. With this we will conclude this section. So right now we are here. So in the rest of today's lecture, we will discuss about, or we will learn about spectral theorem for normal matrices. Okay. So okay, so one thing here, I am not sharing any tutorial sheet, although I am giving exercises during the lecture, but I am not sharing any problem sheet. If you want, I can do that. But my suggestion is that since I am following a textbook like this Horn and Johnson, so you can look at the exercises there in the book, and then you can try to solve them. If you have problem, then we can discuss that. Okay? If you want, then I can also just give you some problems, but my suggestion is that you just try out some of the problems from the exercises. The exams will be based on what we are learning in the class. Paper won't be difficult, it won't be straightforward also, but you will have to use your like the concepts which you are learning in the class. All right, there is one more thing before I start this spectral theorem. I want to have a quiz before minor exam, the first quiz in this course. Since most of you are will be having GATE exam this weekend, so I was planning to have it before, like in this week only. But then some of you requested that can we have it after GATE exam? So that is also fine. I don't want to give you extra burden. So we can do it after GATE exam. That means in the next week sometime, maybe Monday or Tuesday. Not Monday, you can get some time. So maybe we can do it on, let's say, Tuesday or Wednesday. So you can suggest me some time on Tuesday or Wednesday, and then we can have a quiz. So the quiz will be via Gradescope, and I will send an email regarding that, regarding how we'll conduct this quiz. So you can suggest me a day, Tuesday or Wednesday, and also some timing which is suitable to you for the quiz. All right. So if you if you don't propose anything, then I will do it according to my convenience. All right. So what we have done, so I'll mark these topics. These topics have been done, and now we are here. All right. So let us start by defining unitarily diagonalizable matrices. Unitarily diagonalizable matrices. So a matrix A, so let's say let A be a matrix size n cross n over F, where F is either R or C. Okay, then A is called unitarily, or unitarily when F is C, or real orthogonal when F is R. So then A is called unitarily or orthogonally diagonalizable. Diagonalizable if A is unitarily or orthogonally similar to, equivalent or similar to a diagonal matrix. If a matrix is orthogonally or unitarily similar to a diagonal matrix, depending on the field, then we call this matrix unitarily or orthogonally diagonally. So far, you know what is a diagonalizable matrix, right? So you know if a matrix satisfies certain properties, like if it has a complete set of eigenvectors, then it is similar to a diagonalizable. It's similar to a diagonal matrix. Then we call that matrix diagonalizable. But we have seen that not every matrix is diagonalizable. There are examples. Here we will give a class of matrices which are always diagonalizable. So that means if if I give you a matrix and you just quickly check whether that matrix satisfies certain property, that means if it belongs to a particular class of matrices, then you quickly say that okay, this matrix is diagonalizable. Not only diagonalizable, it is unitarily diagonalizable. Like you can find a unitary matrix such that U star AU is diagonal. Okay, so these matrices, so this kind of class of matrices would be called as class of normal matrices. So before that, let us define what is a normal matrix. So we will define it for both real and complex, and whenever a different argument or different statement is required, I'll state that. So let's define normal matrix. What is a normal matrix? Suppose that A is a n cross n matrix over F. F is either R or C. Then A is called normal if A star A is equal to A star. Okay, where star is the complex conjugate transpose. Okay? Complex conjugate transpose. So if this is satisfying, if A satisfies this equation here, A star A is equal to A star, then A is called normal. Now there are certain matrices which always satisfy which always belong to the class of normal matrices or family of normal matrices. Can you give me some example of normal matrices?
Symmetric matrices.
Symmetric matrices. Symmetric, what symmetric?
Real symmetric.
Okay, so you are saying real symmetric, yes. So if you have a real matrix A such that A transpose equal to A, then this is normal. This is real normal. Okay. Anything else?
So unitary matrices.
Unitary matrices. So unitary matrices satisfy this A star A equal to I. So this is also equal to A star, and therefore they are normal. Right. What else?
Hermitian matrices.
Hermitian matrices. So if you have Hermitian matrices, that means they satisfy A star is equal to A. So they are also normal. What else? Some well-known class of matrices which follow this property, A star equal to A star. Like Hermitian, we can also talk about skew Hermitian. That means A star is equal to minus A. So we already know some of the some of the matrices which are normal, well-known matrices which are normal. But there are other matrices, like there are examples of matrices which do not belong to any of these class of matrices here, but they are still normal. For example, you just take this matrix 2 by 2 matrix. This is, you can verify that this matrix is normal, but this does not belong to any of these. This does not belong to any of these 4 class of matrices. This matrix is not symmetric, it's not unitary, it's not Hermitian, it's not skew Hermitian, but it's still normal. So this is normal, but not unitary or Hermitian or skew Hermitian.
But sir,
In fact,
this is a scalar product of a unitary matrix, no?
what is scalar product?
This matrix can be seen as a scalar product of a unitary matrix.
Scalar product of a unitary matrix. What do you mean by that?
Just consider the matrix whose entries are 1 by root 2 minus 1 by root 2 and 1 by root 2 and 1 by root 2. Then if we multiply it by root 2, then we get this matrix.
Yeah, so it is not unitary, that means.
Yes, sir, this is not unitary, but this
Yes.
is a product of unitary matrix to a scalar.
Yeah, it's a scalar multiple of unitary. This is what you are saying. So what I'm saying here, so clearly the columns are orthogonal, but they are not orthonormal. So you can always normalize it by dividing by a factor of root 2. And then it becomes unitary. But this matrix itself is not unitary. That is what I'm saying. That there are matrices. This is one example. In fact, I'll give you one exercise here. You can characterize all normal matrices, all 2 cross 2 normal matrices. So characterize the normal matrices in this. Let's say you characterize all normal matrices of all real normal matrices of size 2 cross 2. So what do I mean by characterize the normal matrices of size 2 cross 2? That means you can say that if you have a matrix A, 2 cross 2 real matrix, then this is normal if and only if these A, B, C, D satisfy certain properties. Then you will see that there are certain, if they satisfy certain conditions, then they belong to, either they belong to one of these class of matrices here, or they are like a scalar multiple or something. Okay, so you just try to characterize. So what you have to do here, so you assume that A is of this form, then you try to do A star A equal to A star, and then see you compare left hand side and right hand side, and then you will get some conditions on A, B, C, D. Based on that, you characterize all matrices, normal matrices of size 2 cross 2. All right, so then there is a nice result. Why we are interested in normal matrices? Because they are like, they form a very nice class of matrices, because such matrices are always diagonalizable. Not only diagonalizable, they are unitarily diagonalizable. So next theorem which I'm going to state, it says that it gives us several equivalent conditions for a matrix to be normal. This result is also known as spectral theorem for complex normal matrices. Similarly, we will state one result for real normal matrices, but let us first talk about the complex result. So this is known as spectral theorem for normal matrices, but I will write it spectral theorem for complex normal matrices because I want to state one more result which is true for real normal matrices. So spectral theorem for, because for the complex case, why I am differentiating these two cases? Because the proof is different for both the cases. One uses the complex version of Schur's lemma and one uses the real version of Schur's lemma. Okay, so if we study them separately, it would be easy to understand, or it would be easy to follow. Spectral theorem for complex normal matrices. So suppose that we have a matrix A of size n cross n over C. Then the following are equivalent. A is normal, which is equivalent to saying that A is unitarily diagonalizable, which is equivalent to saying that the square of the Frobenius norm of A, that means if the entries of A are denoted by Aij, then you look at this sum. This is nothing but the square of the Frobenius norm. You remember what is Frobenius norm? It is trace of AA star. So if this is equal to sum of the eigenvalues of sum of the squares of modulus of the eigenvalues of A equal to 1 to n, where lambda 1 to lambda n, these are the eigenvalues of A. And this is equivalent to saying that there is an orthonormal set of n eigenvectors of A. So this result is known as a spectral theorem. It is like it gives equivalent condition for a matrix to be normal. The proof is not difficult. It follows because of the Schur's lemma. So we'll do it one by one. I'll just give you some hints, but you can verify those things. So we'll prove it like A implies B first, then B implies A, then B implies B if and only if C, and B if and only if. This way we will prove it. This way it is easy also, you will see that. So let us first talk about A implies B. Okay. So let us first look at A implies B. So what is A implies B? So we are given a matrix A, which is of size n cross n over C, and suppose that A, so let A be normal. This is given to us. Now we have to show that A is unitarily diagonalizable. That means we have to find a unitary matrix U such that U star AU is diagonal. Now how to start? How to prove this? But we know it is a complex matrix of size n cross n. So I will just apply Schur's lemma on this. That I can do, right? So because what I need a unitary matrix, right? And we already know that there is a result that says that we can always upper triangularize via a unitary matrix. That is because of Schur's lemma. So we will first apply that, and then we will look at the unitary matrix which we get from Schur's lemma, and then we will see whether that unitary matrix does the job for us or not. Okay. So what we will do, we will apply Schur's lemma. So by Schur's lemma, we know that there exists a unitary U such that U star AU is upper triangular, right? So let's say this is upper triangular matrix T, and the entries of T are denoted by Tij. This is fine. Now, if we somehow prove that this T is diagonal, then we are done, right? Because then we can say that U star A is diagonal, so A is unitarily diagonal. Now we have to show that T is diagonal. So right now we know that T is upper triangular. So that means we have to show that all the off diagonal entries are 0. Now what is given to us? We are given that A is normal. That means A star A is equal to A star. But then this implies that T, so you can say that A is normal implies T is normal. Why? Because you can write A as UT U star. So it would be U T star U star. Then again, similarly, you can write it here U star U T star U star. But then using the property of unitary matrix U, you can say that this implies T star T is equal to T star. So A is normal implies T is normal. Now T is normal means what? So you look at T, what is T? T is upper triangular. So if my T is this one, let's say upper triangular matrix, then T star would be lower triangular. So it would be this one. Then similarly, the right hand side, T would be upper triangular. It would be this one. And then T star would be lower triangular. Right? Now, can you tell me what would be the first entry of the left hand side here? 1 entry. So can you tell me here? This is T star T. So what would be the 1 entry of this left hand side and right hand side?
First,
Can you tell me what would be the first entry? Yes.
T11 square in LHS.
Mod of T11 square. What would be the right hand side?
Sum of
yes.
Sum of T1
Yeah.
T1I square.
Right. Now, if you compare left hand side and right hand side, what do you get? What it gives you? What does this imply?
Sum of square of all other entries equal to 0 except first one.
Yes, so the first entry will cancel out. So from here you can say that T1j is equal to 0 for all j equal to 2 to n. Right? Similarly, if you compare T star T, 2 entry of this, and similarly the right hand side T star, the 2 entry of the right hand side, then the left hand side would be mod of T22 square, and the right hand side would be this one, this summation. But then again, you can say this implies T2j equal to 0 for all j equal to 3 to n. That means this tells that all the entries in the first row of T are 0 except the diagonal entry. Similarly, here it says that all the entries of T in the second row of T are 0 except the diagonal. That means T22. And if you keep on doing the same thing, so that means if you repeat to this one by comparing the nth diagonal entry of T star T and TT star, then this will imply that Tij equal to 0 for all I not equal to j. Okay, but if this is the case, then what does this mean? This implies that this T is diagonal. So this T is in fact diagonal, and this implies that A is unitarily diagonalizing. So this proves B. Now let us prove B implies A. So we have proved A implies B. Now let us look at B implies A. So what is B? Suppose that A is unitarily diagonalizable. Can you say that A is normal? This is not difficult to check. So what is given? Given is, suppose U star A is D diagonal. This is given to us. Okay. Now can you verify from here that A is normal? Can you say from here that A is normal?
So because diagonal matrices are normal, so from there we can conclude.
So diagonal matrices are normal, that is fine. But from here you will say that U star AU is normal if you want to use that. But from there, so you need to say A is diagonal, A is normal, sorry.
Also, sir, U is unitary, so you can post and pre-multiply by U and U star.
Yes. So you can actually have an argument for A. Or you can say that you can just write, since A is unitarily diagonalizable, this implies that A is UDU star. So now you can simply verify what is A star. A star is UDU star. Then this is again UD star U star. This would be UDD star U star. But as you are saying that diagonal matrices are normal because they diagonal matrix commute with its conjugate transpose. So this you can write as D star D U star. Then this is U D star U D U star, which is just A star A. So A is normal. So A if and only if B. Now we show B implies C. So what is B? B is U is A is unitarily diagonalizable. Now we have to show that this sum here is the square of the Frobenius norm of A is equal to sum of the eigenvalues of sum of the squares of eigenvalues in absolute, in modulus. So what is given to us? Given to us is U star AU is diagonal. So let's say this is diagonal and lambda 1 to lambda are the eigenvalues, so they will appear on the diagonal. Now can you tell me what would be the next step here? I need to show that some of the entries, that means the Frobenius norm of A square here is equal to the sum of the squares of these entries here in modulus. So what should I do here? What should I do here? So let me write what it is. So we have to show that this quantity is equal to the sum of the squares of mod of lambda is. So if you look at carefully, this is the Frobenius norm of A square. The Frobenius norm of A square.
Sir,
So what is this?
norms are unchanged under unitary transformations.
Not every norm.
So
You cannot say every
Frobenius,
norms. Yes, Frobenius norm is unitarily invariant that we have seen, and therefore this is same as you can use the fact that Frobenius norm is unitarily invariant, or you can also write why this is true, because Frobenius norm of A square is what? The trace of A star. If you call this diagonal matrix as D, then what would be this? A would be U D U star, and this would be U D star U star. Then this is same as trace of U D D star U star, because this is identity. Now again using the trace property, This is same as dd star u star u. So trace of AB is equal to trace of BA. Again, this is identity. So it is trace of dd star. But then this is the Frobenius norm of d square. But then what is this? This is just this one. So this proves C. So B implies C. Now next, C implies B. So suppose this is given to us. So this is given to us. We have to show, what is our claim? Claim is to show that A is unitarily diagonalizable. Now tell me how to do that. Just tell me the start. If you don't know anything here, just apply Schur's lemma, because it will simplify certain things. It will convert your matrix A into an upper triangular matrix. And then you try to see if you can further simplify it or not. So it will simplify your problem. So far we know Schur's lemma. Once we will introduce SVD, then using SVD you can say many things. So you just apply SVD on a given matrix and see what happens. So your problem would be like simplified in the sense that there would be many zeros in the matrix. So if you apply Schur's lemma on this, then you try to prove. So you apply Schur's lemma and then you tell me how to proceed here. We have to show that A is unitarily diagonalizable. Using the given condition. So if I apply Schur's lemma here, so A is a complex matrix of size n cross n. I know that by Schur's lemma there exists U unitary, such that U star AU is upper triangular. Let's say T. Okay, and since we know that similar matrices have same eigenvalues, so eigenvalues of A are same as eigenvalues of T. T is an upper triangular matrix. So diagonal entries are the eigenvalues of T. A has eigenvalues lambda 1 to lambda n. So T would be of the form this, right? It will have this lambda is on the diagonal. So it is an upper triangular matrix of this form by Schur's lemma. Now I have to prove that this T is actually diagonal. If I can do that, then I'm done. How can I show using the given property here? How can I show that this T is diagonal? That means all these entries are 0.
So apply Frobenius norm both sides.
Yes, apply Frobenius norm, because Frobenius norm is unitarily invariant. So you apply Frobenius norm, let's say square of Frobenius norm. Then what is the Frobenius? What is this left hand side here? This is this one, and the right hand side is just, it is this thing is equal to mod lambda I will write separately, and then plus this remaining term Tij square, where I is less than j. That means the square of these terms here. Now what? What is next then?
LHS is equal to summation of lambda squares.
So that means what? That means these two terms cancel out each other. So this implies summation of this ij square, I is less than j, this is equal to 0. But this implies that all these Tij are 0 if I not equal to j. But then this implies that T is diagonal. So B if and only if C. Now B implies D. So suppose that U is unit A is unitarily diagonalizable. That means suppose U star AU is diagonal, and the diagonal matrix is given by this. These are the eigenvalues of. What we have to show? We have to show. So what is D? Is so D is there is an orthonormal set of n eigenvectors of A. So how to prove that there would be an orthonormal set of n eigenvectors of A from here? What can we say from here?
So since A is equal to U D U star, and we know that the matrix U star, the columns of the matrix of U, they are the eigenvectors of A. But since U is unitary, these vectors are orthonormal.
Right, right. So from here, if you just write U as, let's say, column wise U1, U2, and so on. So these are columns of U. U is an n cross n matrix. So these are orthonormal columns, orthonormal vectors. And since U star AU is equal to D, that means what? That means AU is equal to UD. So if you multiply, if you compare left hand side and right hand side, so left hand side would be U1, U2, so on UN, and the right hand side would be U1, U2, and so on UN, and then this D is lambda 1 to lambda n. You just multiply. If you do that, then you will see that if you compare each column both sides, then you will get this AUI equal to lambda I UI. Since U is unitary, so U is invertible, so all these columns are non-zero. So this implies that these UIs are eigenvectors of A corresponding to lambda I for each I. Now since U is unitary, these eigenvectors are also orthonormal. These vectors are orthonormal. So this implies that UIs are orthonormal eigenvectors of A, and this is fine. This proves D. Okay. Now we have to prove D implies B. Now if suppose A has n orthonormal eigenvectors, how to show that A is unitarily diagonalizable? So what is given? So given these n eigenvectors, these are orthonormal set of eigenvectors. Now we have to show that A is unitarily diagonalizable. Can we do that from here? So can you construct a U such that U star AU is diagonal?
Yes, sir. Take matrix U whose columns are simply U1, U2, and
U1 to UN. So yes. So suppose that these are eigenvectors given to you. So assume that these are corresponding eigenvalues. These are corresponding eigenvalues. So if you set U as he's saying, you just set U as where the columns of U are nothing but these UI, then you can easily verify that AU is equal to UD, but then this would imply that U star AU is equal to D, where D is what? D is diagonal matrix. And you are done. So we have proved spectral theorem for complex normal matrices. So there are several equivalent conditions to say when a matrix is normal. Now there is a nice connection between what we did for um, simultaneous diagonalizable matrices. So if you remember, if we have a family of diagonalizable matrices, then and if that family is commuting, then it is always simultaneously diagonalizable. Now using that, or can you write a similar statement for normal matrices? Can you guess a similar statement for normal matrices? Because you know that now that normal matrices are always diagonalizable, they are unitarily diagonalizable. Can you say something for normal matrices? At least just say, try to speak out a similar statement for normal matrices. We will see whether it is valid or not. But just add something.
Sir, if we have a family of normal matrices which also commute, then we can say that they are simultaneously
Right.
diagonalizable.
Right, exactly. So if we have a commuting family of complex normal matrices, then this is simultaneously diagonalizable. All right. Can you give me a quick proof also? So try to use what we did in at the beginning of today's lecture. So what was the result we proved at the beginning? The beginning of today's lecture, we proved that if we have a commuting family of complex matrices, of complex square matrices, then that family is always simultaneously upper triangularizable, right? So what we can say at least, because this is a commuting family of complex matrices. We will see what normal matrices gives us, but at least we can say from what we know so far that there exists U unitary such that U star AU is upper triangular, or maybe I should not write T. So what I'm saying is that U star AU is upper triangular for every A in this family. Okay, fine. So that means U star AU is equal to some triangular matrix T. Now, what can we say from here? What can we say? So we have not used the fact that A is normal yet. I mean, this family is a family of normal matrices. You remember in the proof what we did in the proof of spectral theorem? If U star AU is T is equal to an upper triangular matrix, A is normal, then this implies that T is normal. So for every such A, this T would be normal. But T normal means T star is equal to T star T. That means T is normal means this condition is satisfied. But if we compare left hand side and right hand side, both sides, what do we get? That implies that T is diagonal. So that means From here itself we can say, so now the normality, the normality implies that P is diagonal, and we are done. So do you agree with this?
So in this result, diagonalizability is unitarily diagonalizable.
Simultaneously unitarily diagonalizable, right? You're right. Maybe I should write it. Yeah, it's a simultaneously unitarily diagonalizable. Sorry. Yeah, thank you. Is it okay now? All right. So far we have stated a result for complex normal matrices. Where is this? But there is a similar result for which is called spectral theorem for Hermitian matrices. As a it follows from the complex normal matrices. But when A is real, then in that case also we can say a similar thing. So far we have stated this result only for complex normal matrices. Remember. Now the next theorem, maybe I'll just state this and we'll prove it in the next class. This is called spectral theorem for Hermitian matrices. So next result is called spectral theorem for Hermitian matrices. So what it says that if we have a matrix A of size n cross n over C, if this matrix is Hermitian, then all eigenvalues of A are real, and second, A is unitarily diagonalizable. In particular, if A is real, is a real matrix of size n cross n and is symmetric, then A is real orthogonally diagonalizable. So what this result says that what this result says? This result says that if we have a Hermitian matrix, then all eigenvalues of A are real and A is diagonalizable. Now, this second part follows immediately because of the complex spectral theorem. That means spectral theorem for complex normal matrices. Because A is Hermitian, so A is normal. Therefore, A is unitarily diagonalizable. So this is straightforward. A is unitarily diagonalizable. That means, so proof is not difficult. Proof is straightforward here. So the second, part 2 follows by spectral theorem, quickly by spectral theorem for normal matrices, right? For complex normal matrices. And part 1 follows because of the second part. So A is unitarily diagonalizable. That means U star AU is equal to D. And the diagonal entries of D are the eigenvalues of A. What we can say from here, since A is equal to U D U star, what is given to us? A is equal to A star because A is Hermitian. So this implies that D is equal to D star. But if D is equal to D star, D is a diagonal matrix. So that implies that all the diagonal entries are real. So this implies all eigenvalues of A are real. So it's very straightforward. Right? Now, in addition, if A is symmetric, then A is orthogonally diagonalizable. So why this is true? This is also straightforward. So if A is symmetric, if A is a symmetric matrix, real symmetric matrix. Now it's a real symmetric, so clearly this is also Hermitian, because if you take the complex conjugate transpose, it star is just transpose, so it is also Hermitian. And because of the the part 1 of this result, you can say that all eigenvalues of A are real. Symmetric. This implies A is Hermitian, and this implies that all eigenvalues of A are real. If all eigenvalues of A are real, can you find the corresponding real eigenvectors, real orthogonal eigenvectors? So since all eigenvalues of A are real, A will have n eigenvectors, complex eigenvectors, but you can always choose n orthogonal real eigenvectors, and then you can form this orthogonal matrix where the columns are nothing but these real eigenvectors, and that matrix can be used to say that U transpose AU is diagonal. So you just verify this, and if you have any doubt, you can ask. So since all eigenvalues of A are real, the corresponding eigenvectors may be taken be real. Why this is? Because if A is real, and even if X is a complex eigenvector, that means if it is of this form, and lambda is a real eigenvalue, then this implies that AX1 equal to lambda x1 and AX2 is equal to lambda x2. So that way you can always choose n orthogonal, n real eigenvectors. You can always orthogonalize it using Gram-Schmidt, and then you can construct your matrix for this real orthogonal matrix U such that U transpose AU is diagonal. Okay, so it's time, so we can stop here. And in the next result, we will prove spectral theorem for real normal matrices. So if you have any doubt, you can ask. Otherwise, we'll stop here. Well, you can also suggest me a day for the quiz, whether you want it on Tuesday or Wednesday. Next Tuesday or next Wednesday. That means the next week.
So Wednesday evening.
Wednesday evening. Okay, so Wednesday 6 o'clock. Is it okay?